In general, the grades were pretty decent. I think the class average after the curve was an 80. So, assuming people would have botched that question anyways, even if I had covered it, it's about a 70, which is where probably grade should be. But so, fairly happy with the grade distribution. So, if you, after your 10 points, if you cleared an 80, you're ahead of the class average. If you got substantially less than that, I guess suck less next time. Remember that you do have an opportunity for, in all my classes, if you do better on the final exam than you did in the midterm, I'll replace your midterm exam grade with whatever you get on the final. Not the other direction though. You don't get to do great on the midterm and then suck on the final. So it's so you get a get out of jail free card. So if you struggled on this exam, I don't think one day of one bad performance should really screw your grade over for the semester. So hopefully some of you agree with that. Okay, so let's go ahead and go through this. Just throw it down here at the bottom. So this is midterm. So midterm number 1 says, what does it mean for Java to be platform independent? So that's the write once, run anywhere, runs on a virtual machine, compiles to Java bytecode, which the Java virtual machine knows how to run. JVM is ported to the various platforms like Windows, Mac, etc. So some combination of that stuff, all right, is kind of what I was looking for there. Okay, questions on that one? I think most people got that one right. If you missed that one, that's probably shouldn't be too happy with yourself. Midterm number 2, convert. 1001101 from binary into decimal. All right, so I'm going to space this out a little bit. All right, this is the ones place. This is the twos place. This is the fours place. This is the eights place. This is the 16s place. This is the 32nds place. This is the 64ths place, and this is the 128ths place. Whatever, we need to space it a little better, but we'll just leave it at that. So wherever we have a 1, we need to do the adding, right? So 1s place, 2s place, 4s, 8s, 16s, 32s, 64s, 128. So we have a 1 in the 128, so this is 128 plus, let's just go. I got to go the other direction so I can read it. So this is 1 plus, this is the 2's place, this is the 4's place, 1 plus 8's place, 8 plus 16. So 1s, 2s, 4s, 8s, 16s, 32, 64, 128 plus 128. So that's 157 in decimal. All right, so technically, if you were to go through this is 128 times 1 plus 64 times 0 plus 32 times 0 plus 16 times 1 plus 8 times 1 plus 4 times 1 plus 2 times 0 plus 1 times 1. So where all the zeros are in there, we can kind of skip those. All right, questions on that one? All right, number 3, how does Alice mimic a human being's ability to ask questions? So conditionals or if statements. something along those lines. If you started babbling about Boolean expressions, I pretty much took most answers that involved that, as long as you kind of wrapped it back in. Questions that really weren't right was like functions and procedures, or answers that were not correct, or when you're talking about functions, procedures, that kind of stuff. So, you know, this question was connecting us to how human beings solve problems in terms of memory, asking questions, and repetition, and how Alice fulfills those three things. We mentioned every single programming language has facilities for accomplishing those three things. Specifically, Alice accomplishes asking questions through conditionals, which is the if statement, if else thingy. Make sense? All right, questions on that one. If at the end of class, after class, if you think I ripped you out of points or something, let me know. I'll take a look at it. If you think I gave you too many points, let me know that as well. This group wouldn't even tell me when I forgot to put a homework assignment up. I think there's a pretty low chance that it's like, are you sure you didn't give me too much on this? This answer doesn't seem right. I've never had a student do that. So, who knows? Maybe you'll get extra credit. Fishing for this. All right, number 4. Describe the difference between a procedural language and an object-oriented programming language. So this was kind of when we talked about the telephone. So either a pile of wires or it looks like a telephone, but all the stuff is kind of shoved inside. If you put it into some words, you might say procedural languages tend to be monolithic in nature. Where everything is, well, maybe where all the details are visible and presented in a linear manner. Object-oriented tend to encapsulate the details within an object, maybe object container, and only exposes the public interfaces that are required to use the object. Something in that ballparky type of thing. Questions about that one? All right, number 5. What is an array and why do we need them? So this is a variable type with a single name associated with a collection of like values. So for example, we had in our tic-tac-toe game, we had a collection of Monkey Kings. That was an array of Monkey King objects. We could have an array of numbers, and I give you one of those in number 10. That's an array of numbers being passed into that. So this is a variable, which is mimicking memory, capable of holding more than one value of the same type associated with a single variable name. Right, so something along those lines. Yeah, so that's that one. Questions about that? All right, so that's what an array is. All right, now, before we can answer midterm number 6, we need to talk about that. We need to introduce that concept. This really belongs somewhere inside of the, when we first started introducing Java and the idea of a strongly typed versus a loosely typed language, how we have these primitive types built into Java. These really came from C. So the folks who got some points for this question are the ones who kind of related it belonged in that evolution of languages discussion. All right, and I want to say at some point we did kind of discuss it at some sort of high level, but it didn't make it into the notes. And given the fact that literally everybody missed it, nobody got it completely correct. We clearly did not talk about it enough. So we go back to a. Did anybody get full credit on it? I don't think anybody did. You got full credit on it? Really? So you missed something? Huh. Well, you'd see like a minus next to like minus points on where your answer is. Yeah, so it's possible. But let's talk about this. So the idea is that our we've made this argument that our modern languages are all based off of C, right? So any of our modern languages, they all look like C because they came from the C language. And we were talking about the evolution of those languages. So if we talk about variables in C, and this goes back to, remember when we talked about the evolution of C specifically, we talked about, I like looking at that through the lens of variables. Thinking about C, it provided normal variables, it provided arrays, it provided structs, but came up short of having a class and that kind of stuff. But our primitive type variables in C are byte, short, int, long, char, float, double, and Boolean. Okay. Now, these are all the various types in C, which are also the types in C++, which are also the types in Java. So these Java supports this exact same guys here. Now, when we're talking about Alice, we think of the types we've seen in Alice are whole numbers, text values or text strings, something like that. We have a smaller subset of types. But in our historical languages, and then through to our modern languages, because they've all inherited this stuff, we have all of these different variable types that are built into the language, okay, for types of values that we can hold. Now, to talk about each of these, a byte holds whole numbers. A short holds whole numbers. An int holds whole numbers. A long holds whole numbers. A char holds whole numbers. And then these guys down here hold decimal numbers. And then this guy is true false for our Booleans. All right. So what this question was asking is, why are there so many ways of holding whole numbers? Why are there so many of those guys there? Okay. So let's talk about each of these. Give a little more detail to it. So a byte is a signed 8-bit number. A short is a signed 16-bit number. An int is a signed 32-bit number. A long is a signed 64-bit number. A char is an unsigned 16-bit number. Now, when I say signed versus unsigned, signed numbers are capable of holding both positive and negative values. All right, so even though this number is represented as 8 bits, only 7 of those bits are used to hold the value of that number, because one of those bits is reserved to keep track of whether it's positive or negative. So in this unsigned value down here, and we'll talk about these in more detail here in a second, in this unsigned value, only positive numbers are capable of being stored. We don't maintain the sign. So we get all 8 bits to hold the number. Okay, and when I say 8 bits, so if we just do something like this, so an 8-bit number is a number comprised of 8 zeros and ones. So our smallest 8-bit number is that. Our largest 8-bit number is that. Now, this is if we're dealing with an unsigned number. If we're dealing with signed numbers, this far left bit is used to keep track of whether it's positive or negative. So we only get 7 of these numbers to actually represent our value. All right, so if we think about that for an 8-bit number, if we have a 1 followed by a bunch of zeros, Actually, we'd just be 7 of these guys because we're dealing with unsigned. Okay, this is stored in something called 2's complement form. Not important for us in here. We talk about that in 325. But effectively, this number is negative 127. That's what that number is. As opposed to that number, which is in 2's complement form, which is the number positive 128. Okay, you have to convert it into away from 2's complement form. But what's important here is only 7 of these bits are actually used. And let's see. Yeah, that'll work. All right, so if we kind of come back to this map here, a signed 8-bit number is negative 127 to positive 128. That's the range of values that fit inside of a byte. All right, let me just put that in parentheses so it's a little cleaner. Range of values that fit inside of a short. This is plus or minus. So for a byte, plus or minus 2 to the 7th power. Plus or minus 2 to the 15th power, because one of the bits is used for the sign. So this is negative 32,767 to positive 32,768. That's the range of values that fit inside of a short. Okay, a int, this is negative 4.2 billion to positive 4.2 billion. That is plus or minus 2 to the 31st power. And so if you want to see that, here's 2 to the 31st. So that's your, what I estimated to be 2.2 billion. 2.147 billion is the actual value. 64-bit number is negative, big num, to positive, big num. I think it's something like 4 quintillion. So this is 2 to the 63rd power. So 9.2 quintillion. That must be big number. Okay, big number. But not an infinite number, because in Java we do have objects that allow. We have an object called big integer that allows us to have numbers that are larger than would fit in a long. And as you get bigger and bigger numbers, the performance goes down, but you can represent huge numbers. All right. Finally, this unsigned char thing, this is 0 to 65,535, which I think you'll find if you take the absolute value of both of these numbers and add them together, you get that. All right. So this is the same as our signed 16-bit number, except we don't have to store negatives. So this is 0 to 65,535. And what that's actually related to is this conversation of ASCII versus Unicode. So ASCII is American Standard Code for Information Interchange. So ASCII has 256 unique character mappings. So for example, I'll just show it to you real quick. So we have a whole bunch of numbers between 0 and 255, and each of those numbers map to exactly one character, like A's and B's and question marks and commas, and then there's like smiley faces and playing cards and stuff like that. So let's see, is it actually going to load something? Yeah, here we go. So 0 is the null character. Blow this up a little bit. ASCII 32 is the space. ASCII 33 is the exclamation point. Less than, stuff like that. So the first 128 characters are stuff that we recognize, and then you get to some weird stuff. So like here's the mu character and sigma and pi, some square root symbol, stuff like that. Yeah, so those are the extended ASCII. But the idea here is that in early let's say early software applications, as Americans tend to do, we think the world revolves around us. So given that, why shouldn't only our characters be represented, right? There's probably some stuff written on the wall in that Guatemalan prison that wasn't on this ASCII chart. Okay. Okay. So, actually, you might have had a couple of them here. All right. So in any case, as the world economy kind of evolved and the internet took off and that kind of stuff, and we started seeing a need for representing characters from languages all over the world, that's when Unicode stepped in. Unicode is a superset of ASCII. So the first 256 characters of Unicode are identical to ASCII. They just took this table and it added more. That is symbols from all sorts of languages in the world. It's not necessarily all of them, but a lot. Okay, so we have 65,536 unique symbols on the Unicode character set, the first 256 of which are from ASCII. All right. Now, having said that, let's kind of go back to this idea. That's what Unicode versus ASCII is. Unicode has 65,536 unique character mappings. It's a superset of ASCII. All right. So kind of coming back to this slide here, chars are actually represented as whole numbers. Okay, because computers like numbers, people like characters and stuff. So what we do is when we store a character inside of a programming language, what we're actually doing is we're storing a numeric value that will ultimately be mapped to an actual character on either ASCII, if we're going back to older languages. C and C++ used ASCII, Java uses Unicode. So it'll map to a larger thing. But the idea here is that at runtime, the computer is doing that mapping. It's taking the if it notices, and this kind of comes back to this idea of a strongly versus loosely type language, which we'll talk about here in a few minutes. If it notices that you're storing something as a char, it knows it has to do that conversion because you've specified that the kind of value that's stored in that variable is a char. And even though that value is under the hood represented as a number, it needs to be mapped to its equivalent character at runtime. That makes sense? And it does that by looking it up on ASCII or on the Unicode chart. So that's why chars are also stored as whole numbers. All right. Now, question number 6 really involves these guys right here. Okay, those 4. So why do we have 4 different ways of holding positive and negative whole numbers? That's really what I'm asking. All right, and this goes back to did we talk about the Y2K bug? Yeah, see, this is that section we skipped. Okay, something happened. Who knows? Okay, well, but I didn't cover it. I don't trust that class worth anything. So, was that out loud? All right, so in any case, what is the Y2K bug? So there's probably something that most of us have at least heard of that phrase before, right? Just like most of these technological buzzwords, we've heard of things, but sometimes we don't know what they mean. So what would you say it is? Go ahead.
People were afraid that computer systems would have major malfunctions when the year 2000 came around.
Okay, so like Terminator Judgment Day type stuff?
I'm not sure on what scale.
So why? Why were we concerned? What was the underlying problem that we were concerned was going to show its ugly face?
I'm thinking about some type of code only going to 1999.
Okay.
2000. I can't remember.
Okay, well, we're on the right path there.
Didn't they store years of just the last 2 digits?
Yeah. Yep. So, older software stored years as 2 digits. So the Y2K bug was what happens, what is the difference between 1900 and 2000 when they both look like 00. Make sense? So all of a sudden, all these things that were sorting on dates and stuff like that wouldn't be sorted correctly anymore once we started hitting 2000. All right, so the real question here is why did older software store years as 2 digits? It didn't take up as much space. Okay, so why was that a problem? Why was that a big deal? Was space a problem? I mean, you got a laptop? Okay, how much memory is in your laptop? Yeah. 8 gigs of RAM. Okay, so do you ever run out of RAM? No, you got plenty of RAM, right? Okay, even you go out and get a budget pleaser laptop today, it probably comes with 4 gigs of RAM. Okay, lots of RAM. So who cares about 2 digits versus 4 digits? Even if we store everything as a 64-bit number, which can hold what, the 9.2 quintillion, okay, is a 64-bit number. If you have 8 gigabytes of memory, let's walk backwards here. So 8 gigabytes of memory, we want to know how many bits that is. Okay, so 8 gigabytes we're going to multiply that by 8 to give us gigabits, right? Well, here, why don't we walk up the scale and then walk down? So 8 gigabytes is how many megabytes? That's 8 times 1024. So that's 8192 megabytes. 8192 megabytes, which is how many kilobytes? Times 1024. That's 8,388,608. 8,388,608 kilobytes. Okay, then we multiply that by 1024. That's bytes. I'm not going to write that one down. Okay, that's bytes. Then we multiply that by 8. That's bits. Okay, that's the number of bits that your 8 gigabytes of memory can store. Divide that by 64. Okay, that is the number of longs, the number of 64-bit integers that you can hold in your computer's memory. So this is 741,000, this is 73 million, this is 1,073,741,824 numbers. How many numbers do you think your computer needs to store for your average piece of software? So we've written tic-tac-toe and stuff in here, and so what we've had 5, 6 variables in our programs, 5, 6 numbers. Okay, so now let's translate that into like a big operating system. Do you think a big operating system actually needs to store 1 billion numbers? That's a lot of numbers, right? So today we can be completely inefficient. We don't care. Plenty of space. And if we run out, what do? Just run over to Best Buy, pay retail, and we could double our memory for 50 bucks. Right? No harm, no foul. All right, so let's travel back in time for a moment. So we'll go to 1996. How many of you most of us were barely alive in 96 probably? Huh? 1? Any of you not alive in 96?
I was born in 96.
Born in 96? So it depends on date.
Yeah, part of that.
Okay, so you were very young. Okay, you were at your prime, young, fresh. Okay, so no injuries. We're just good to go. All right, so in 1996, let's talk about a computer I had in 1996. I had a 486 DX2 66 megahertz computer. This guy had the math coprocessor. Sick. And this guy shipped with 8 megabytes of RAM and a 420 megabyte hard drive. All right. So I decided, you know what? What are the cool kids doing today? They're doubling their system RAM. So I wanted to go from 8 megabytes to 16 megabytes. Now, if you go to Best Buy today and you buy what, 4 gigabytes of RAM to take your 4 gigabyte laptop to 8 gigabytes, it's like 50 bucks. Probably get it less online, but let's just say it's 50. Okay, so today 4 gigabytes of RAM is $50. Okay, now I want to take 8 megabytes of RAM and turn it into 16. So I need to buy 8 megabytes. All right, so first of all, how much bigger is 4 gigabytes than 8 megabytes? So that's 4 times 1024, that's 4096 megabytes divided by 8. So it's 512 times the size. All right, so a budget pleaser laptop today with 4 gigabytes of RAM in it has 512 times the amount of memory than my computer did in 1996. Okay, so how much was 8 megabytes of RAM? Well, if we say by today's standards that 4 times 1024 is 4096, and we divide that by 50, actually we take 50 and divide it by that, right? That's about a penny per megabyte, about a penny per megabyte. So by today's math, roughly speaking, 8 megabytes of memory should cost me less than a dime, right? Somewhere between a dime and a nickel, right? How much do you think 8 megabytes of RAM cost me in 1996? Say this again. $700? Nope, too low. It's too high. So it's about $1,000. $1,000 was 8 megabytes of RAM back then. So that's 1,000 divided by 8. That's $125 per megabyte compared to a penny per megabyte today. And you got to keep in mind that that's not even taking into consideration inflation, right? It would have been even more expensive. $125 back then is more than $125 today, right? So you got to do the whatever the inflation values are. So with that in mind, memory was really expensive. Now I can tell you that in 1996, the price of memory had already been coming down drastically. It was even more expensive before that. Okay, this was considered reasonable. Right, this was considered reasonable. So you go back into the 80s and late 70s. So like C came out in basically C was like 1968. So back then, memory was prohibitively small and ridiculously expensive. So maybe you would have paid $500 for 1 kilobyte of memory back then. Very, 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 very expensive. Okay, so memory was a lot smaller. It was really, really expensive. So we couldn't store enough numbers to begin with because we didn't have enough real estate. We didn't have space, regardless if we had the money. Okay, and then even if we had the money, we would still want to be good stewards about this because, well, the space was equal to money. So they decided to start storing things that they could represent in smaller pieces of information. They would store in smaller containers. And that's when they decided to store years in 2 digits instead of 4. Because the idea was, oh, by the time this is a problem, we will have replaced all of this software. Well, that ended up not being the case. For as an example, my wife is a COBOL programmer. So she programs in a pretty old programming language, and she works at Western Illinois University. And she worked remotely out of her house there when we moved. But she maintained software that was written in like the 1970s and 1980s. They write new stuff today, like they're writing, they're doing dynamic web pages backed by COBOL, which shouldn't be a thing, but it is. That's why IBM is still in business. So IBM used to be the cool kid back in the 80s, and now they make all their money off mainframe software and mainframe hardware, and then conversion tools that allow really old technologies like COBOL to still be used today. because you have a bunch of companies out there, a lot of insurance agencies and a lot of banks have spent millions of dollars over the years writing a whole bunch of software in very old languages. The software still works. It doesn't look pretty, but this isn't customer facing. You know, this is somebody working at the bank. You've probably been in a business before, you know, whether it's a bank or an insurance company or something like that, kind of like, you know, the old stuffy type of big businesses that have been around for, you know, 100 years, where even today you see somebody working at a computer where everything on the screen is like a text terminal. You know, that might look something like this. You know, they're typing in commands into this thing and seeing stuff come back out. That's probably some program that still works great that was written 30 or 40 years ago. Why fix it if it's not broken? But you still need people who can maintain it. So that's kind of where COBOL comes in. So, you know, the idea is that our older languages, when we were writing that software, we assumed that that software would be replaced before it was a problem, making those choices to store stuff as 2 digits instead of 4. Well, in many cases it wasn't. So that's why the year 2000 was kind of exciting. I remember sitting on the couch. Like now when you watch New Year's, you know, it's where you watch the ball drop, right? All 3 or 4 different. Usually it's like you watch it in Paris and Sydney and stuff. The different celebrations, the big ones. You don't watch some podunk town in Texas's celebration. So you watch a couple of the big ones. Well, back then, I remember it must have been like 17 hours of coverage. And I think the very first country was that hit midnight is somewhere in Australia, I think. And so I remember they basically just had a still camera, okay, just on like their power station, just seeing the lights go out at midnight. And then after that one didn't, they moved to another. They just had cameras that you would sit there for 45 minutes just waiting for the clock to tick, staring at like lights just to see if they were going to go out at midnight. So and I sat there for 17 hours. It was a very interesting drinking game. So, yeah. In any case, that was the scoop with that. So that's kind of our punchline. So the reason we have so many different ways of holding whole numbers is because our older languages needed to give a programmer the flexibility to make the best decision for the kind of value that we were going to have to store. If we knew we were only going to use the numbers between 1 and 10, why not store that inside of the smallest container possible? Right? Today, as programmers, we don't really do that. That isn't to say that we should just go out of our way to be inefficient, but generally speaking, as a programmer today, Java programmers, if you need to store a whole number, you use an int. If that's not big enough, you use a long. If that's not big enough, you use a big integer. Nobody uses shorts anymore, so it's a waste of time. So if you ever are looking at code on Google that uses a short, it's from an older language. Bytes are still used, but for a different reason. So bytes, that's the kind of when we have streaming media, like video and audio streaming, it usually comes in as a byte stream. So we'll take it in 1 byte chunks. So a byte just happens to be the right size container for us to process a media stream like that. All right, so that's kind of why bytes are still used. We don't use bytes because, oh, well, I only need to hold the number 10, so I'll just throw that in a byte. People will laugh. All right, so that's why we have so many different ways of holding whole numbers. So could have said that a bunch of different ways, I suppose. If I steal this. So it's midterm 6. Y2K stuff. All right, so what we just really talked about. So let me keep trucking here so we can finish going through the exam before we're out of time here. Midterm 7. What does it mean to compile a program? Convert from high-level language to low-level language. All right. So this happens prior to runtime. So something along those lines. Number 8, what is the difference between a strongly typed and a loosely typed language? Strongly typed languages like Alice and Java require that we define the kind of value a variable is built to hold. Loosely typed languages do not. All right, so all the languages we've been introduced to are strongly typed languages. The other guy, when we were talking about some of our web languages way back when we talked about kind of the history of our languages, a lot of those guys are loosely typed languages where we can put anything we want into a variable. All right, write an error-free hello world program. You can do that. Actually, most people did well on that, so that was good. And then finally, midterm 10, the very last one. What would the output of the following code be if the input was that array? So if you go through there, what this array, what this code does is it looks for every number in that array. So it looks at 1, then 3, then 4, then 8, all those numbers. And for each one of them that is evenly divisible by 3, it adds it to a running total. So x starts off at 0, it's our running total. And then every single time we have a number that is evenly divisible by 3, we add it onto our running total. If it's not evenly divisible by 3, we added a 0, effectively ignoring it. Okay? So that means out of this list, what are we adding? We're going to add 3 plus 21 plus 24 plus 30. So those are all the numbers from our array that are evenly divisible. So that's a 78. So the output of that function would be 78. We're ultimately returning x at the end, which is the sum of all the numbers that were evenly divisible by 3, which is 78. Make sense? All right, so that is the midterm. If you have any questions about how I graded your specific exam, feel free to come up. I'll hang out for a few minutes. Otherwise, we'll continue on with our Java stuff on Friday. We don't. Well, I'm going to continue on Friday. So I guess we have class Monday.
No, Wednesday. Easter break. Friday and Monday.
Friday and Monday, Easter break.
Yeah.
Man, I should have stayed in Florida. What was that? I could have gone to Guatemala and chill. All right, I guess Wednesday.
You don't want these back.
No, they're yours to keep.